imaging devices. And now I'm at Micron, and what I'm doing there is I'm leading an architecture on emerging technology. I can't really talk about that. But I'm going to talk about some other things that kind of hover around some future computer architectures. And specifically, I want to spend some time talking about computer architectural disasters and failures. And it's fun to do that. And maybe we can learn some. We're going to try to get this thing to work. There we go. So, yeah, I'm going to start out by talking about some flops. Not CPU flops, but actual failures. I want to talk about the current state of compute, where problems exist and what we're doing on it, and some emerging trends. And there's a picture of a Turing machine that was not a failure. So, what I wanted to do was kind of get a roadmap of what I consider, and this is an eye chart, to be some of the fundamental breakthroughs in computer architecture that persist today. And what I don't want to look at are academic pursuits. I mean, academics are interesting, but they don't always lead to a market success. So what I want to look at are market successes that still exist. And I go back all the way to 1961, when a little company called Burroughs actually came up with a technology called virtual memory and paging. And that was kind of the first instance that a customer could buy a paging system. So that's something that stuck with us. And then we see this era here in the late 60s, early 70s, when we owe quite a bit to a company called Control Data. And Control Data was under a lot of the leadership of Seymour Cray, when he worked there. And there are things that exist in computer architecture that are still persistent. For example, out-of-order execution, scoreboard, superscalar pipelines. We see the first pipeline processor from CDC in the late 60s. The first TLB for on-chip caches came from IBM. And the first vector machine, we talk a lot about vectors, came out with the Star 100 from CDC. So we owe a lot in a typical microprocessor today to what Seymour Cray did at Control Data. So then he leaves. So the late 70s into the 80s was the Cray era for high performance computing. But there's some other things that popped up. The first commercial microprocessor, Intel 4000. Actually, that's too basic. And what we also see is the first DSP. The first DSP is a really interesting piece. It's this guy here from TI. And the first DSP wasn't actually used for anything significant in silicon. It was actually used within TI itself for the speaking circuit. And shortly thereafter, AT&T created a version of it called the DSP-11. And that formed what's essentially the ESS switch in modern telephones. In the 80s, this is a ripe area for computer architecture. So what we saw in the early 80s was a device called the transputer. And I'll talk about that. We saw MIPS and RISC technology, first VLIW processors in multi-flow, the first FPGA was designed. The first true SIMD machine for thinking machines was created in the early 80s. And I wanted to go back and actually look, well, when was the first GPU? Everything is done with GPUs nowadays. There's CPUs and GPUs and that sort of heterogeneous system. I actually came back to the first programmable piece of graphics hardware was in the Amiga with the Agus and Denise chips. And we also have reconfigurable computing. And then there's a gap in computer architecture in the 90s. So a lot of foundation work happened in the late 60s and the early 80s. And so the question is, well, were they all successful? So why didn't these architectures review some architectures with some companies? And it's not necessarily the technology. It could also be the time to market, and competition. But do they leave anything with us? So I created some chart here couldn't find a graphic, so I created one, and I call it the Dead Computer Society. And there's some really great companies. There's a number of machines that I see. There's SIMD machines, so that's single issue, vector machines that control data and create kind of network. That's interesting. And you see those symmetric multiprocessing unity machines. And these actually, this kind of stands alone today. You still see some SMP machines. You have this weird thing here called a transputer. You get this really bizarre stuff. Type of computers, real life cores, and a really bizarre machine, avant-garde architectures. So some of these still exist. Great research that formed into what's now Cray incorporated after the University of Era. Intel exists. Well, that division doesn't exist. That was Intel Scientific Computers, created hypercomputers. All of these are essentially dead markets and dead companies. So why did they fail? So I'm going to talk about the most famous failure in computing history. And that was a my quote. That was from MIT. And it's really interesting who that would be. You think, well, what kind of company failed? And the company there was thinking machines. And this was I don't know if anyone has ever seen one of these machines. It's in a box. It's called a blinking light machine. It stands about this high. It's a cube. That machine was basically based on Danny Poston's PhD work. And they got some seed money. Actually, the seed money came from CBS. And it's essentially an array of these very simple computers connected in a hypercube machine. And it used very simple computing, near memory microprocessors. Memory and the microprocessors were one. And they could get up to 20 gigaflops, and the revenue was about $65 million. So this was the first machine that was purposely built to solve AI problems. AI is a really big topic today with machine learning, convolutional neural nets, and whatnot. This was the first purposely built machine to address those types of problems. So they brought to us factory networking for hypercubes. They combine SIMD programming with Unity programming, but they are the most famous failure. And the way they started is they started without any business. They started with the notion of we have a technology that's really cool, it might be applicable to artificial intelligence, and let's do it. And they made wild claims about the capability. We'll build a machine that will be proud of us, was one of their models. And that never happened. And they also made a claim that, no, we can have one of these machines in all of these different regions, and people can actually use their dial-up, call into the machine, and use it for AI purposes. And that was their business. That essentially didn't happen. Supercomputing is a technology, not a business. That was actually what Phyllis said in reflecting on how this machine and this company died. We were a supercomputer company. No one makes money being a supercomputer. And the reason is that there was a complete reliance on DARPA funding. And without that DARPA funding, it was essentially an academic exercise. And the final thing that killed it was years of emotional and improper management. And the company was going under, and Cheryl Handler, who was the CEO at the time, I equate her to Nero as Romberg, because she was actually producing cookbooks of the cafeteria food while the whole company was following each other. So this is a complete failure with brilliant technology and technologists. So some other ones that are equally as interesting as NASCAR. NASCAR was founded by a guy out of Denver. You're going to see a Digital Equipment Corporation actually seeded a lot of different other computer companies. This was a SIMD architecture, so single instruction, multiple data, and it was scalable. It actually was designed for scaling up front. It used custom logic. It was staffed by TI and industry at the time. And you could program it using standard tools, Fortran or C. The one thing that they claimed is they did have a business plan. The business plan was that this was going to be a general purpose computer. They also made claims that it was going to be a $1 billion market in 10 years. So what did they give us? In short, they gave us SIMD machine versus pre-vector machines. Everything was a vector computer, and that's what Signal is. This was also the first RISC-like ISA supercomputer. That was scalable architecture. It was also one of the first architectures that commercialized what we call Harvard architecture for general computing. So why did they fail? Well, this was the DARPA dilemma. You're going to see another company shortly called banquet, which I've used their machines. They criticized thinking machines because they actually never could get DARPA funding. And without that DARPA funding, without that seed money, they were on the path to failure. They kept telling their analysts, they kept telling their investors that this is a fundamental computer architecture that would prevail, turn into consumer devices, desktop computers at the time. And that never happened. It was hard to actually take a scalable architecture, these are multi-million-dollar machines and scale it into something that's consumer. This is a really interesting company. This is Multi. It was founded by Josh Fisher in '84. And he came out of Yale. And the whole idea here is it's a VLIW machine. So put all the reliance on the machine performance on the compiler, on the software side. And it was the first VLIW machine, the first VLIW that was marketed. This is one of the marketing plans. The device sold about 125 units. They were between 300K to $1 million per device. And they had some respectable performance. The company only netted about $50 million. So originally, they were a startup, and they were formed as a startup. As a matter of fact, Josh's wife wrote a book on how to run a startup business. That's the stuff here. Multi-core computer startup Odyssey. And they were hoping to get bought out. And originally, they wanted to give a mission on Apollo. Later on, they were trying to get bought out by DEC. And that did. Not that they closed their doors 2 days later. The whole performance was built on a compiler. And their business plan was that, again, they touted this thing as a general purpose computer, not just a supercomputer for HPC needs. And that never happened. So, again, the money ran out. They didn't get the DARPA funding they needed, and they never formed into consumer products. I want to throw this one in there because this is a company, Encore, that was founded that doesn't exist in 1983 by Gordon Bell, just some brilliant guys. You can't go wrong with your founders coming from DEC and trying to do it. So they created a machine called System 91, System 91, and it used off-the-shelf boards that had a respectable amount of memory and respectable computing power. Again, it was scalable from $50,000 to $1 million per year, on that multi-phone. And they got about $250 million in business. They were the early pioneer in symmetric multiprocessing and shared memory. So what they gave to us is basically things like fault tolerance, memory, and they essentially invented bus systems. You have a cache, again, their business plan was, we're going to take over the world. We're going to be in every PC, in every mainframe, and we're going to saturate the HPC market, and we're going to reassemble this. Well, that didn't happen. So they refocused and said, we're going to make a real-time machine on this thing. We're going to handle air traffic control. And so they bought the company to take their technology into the real-time business, and they never financially recovered. And finally, the quality was the first designs failed in consumer goods. As a matter of fact, you can go to a website now, and there's a small outfit that will actually service your own machines. NQ, this is an interesting one because this was formed from ex-Intel engineers out in Hillsborough, right here in Oregon. Where are you? So they commercialized hypercube architectures, and they did this pretty successfully. They could never really generate any kind of revenue. The machines were beasts. They get 127 gigabytes theoretically. Practically, they were about 2 gigabytes. And we only saw about 100 of these units to universities or government labs. And they successfully took a technology and mass produced it, and they did it well. Their biggest failure was they could never get DARPA funding. And they actually argued this quite publicly, that the DARPA funding was being channeled and funneled into thinking machines. But thinking machines had a very limited use. A machine like this is more general purpose. So they and other companies felt shortchanged because they could never see that funding. And there was a lot of hubris there. Their claims were that, again, they had technology better than a connection machine and equally better than a code for a portion of the cost. And again, they thought they were going to take over the world with technology. So the lack of DARPA funding and the essential lack of a good business plan really affected them. Where they are now is really interesting. Some of their technology still exists. And I told you I was going to talk about transputers. And one of the big centers for transputers was in the UK. Transputers came out of the UK. Essentially what a transputer is what you see today. You have a system on a chip with a processor or a mix within the silicon to connect to identical machines. So you could grow a more complex and interesting topology of these transputers. Essentially it's a bus. So this company called Micron, which produced devices called computing services, used transputers at the heart of their machine. What was really interesting about it is it was half a transputer and half an Intel IA system. The other really significant thing that amazed me is after they got their initial funding, they produced a demo machine in 9 weeks. And demoed it at SIGGRAPH, which is unbelievable. It's pretty the number of machines sold is about 250 in respective performance every state. So they were a pioneer in transputers, but their problem here is that their machines, again, were sold to UK government audiences. They never became profitable. They could never scale this transputer down into commercial. And as soon as we got to moved away from proprietary bus architectures to more mainstream bus architectures, And again, they have behaviors that say, well, this technology is going to do that. So, the dead computer system. Where are they now? So, thinking machines basically responded to 83 in filed chapter 11 and 94. Total employee count, highest employee count is about 400, mostly in Cambridge. And where are they now? Well, the rights to a lot of their IPs are in some Oracle. NQ is interesting. They built those distributed hypercube technologies. They lasted until about 2005. And now they are actually, a lot of the IP, software IP, is used for IP for video on demand. Mako, the integrator of transputer architectures, they lasted until about 2003, stations to 2009. And they were bought by Quadrix and then Quadrix. Multiflow is interesting. DLIW processors really never became general purpose. They were used in additional signal processing. And actually, a lot of that IP was purchased by HP and then resold into ST. NASCAR, they lasted until 1996. 9-year run. Remnants of their architecture is indeed a mining software. And on-board computer, shared memory, NIMD machines, the only remnant of on-board instances was purchased by Sun, and that's their storage controllers. So there's lots of other failures. Perry Research, Kindle, Convex, supercomputers. I'm not going to go into all of them. There's a resonant theme, and that is, this is the top 500 computer list. It was back in 93 and goes into about 2013. And the interesting thing here is that you see 17 unique designs and architectures that we make early years. And today, there's only 5. And the 5 that exist are dominated by Intel Xeon Type 4s, IE32, just standard off-the-shelf Intel cores, and a smattering of others. So the early 90s was a good space to invent and nurture different computer architectures, but eventually only 5 are left standing. So what do you learn from that? Is that supercomputing is fun and interesting, a fun playground for avant-garde architectures, but it isn't economically viable. If your business model is sustained by DARPA, that won't last. If you're designing a supercomputer, it's more or less using special things, machine. You can't really say that it will extend into a consumer market or mobile market and have a good management also. So those are my groups. If you ask someone who's a little more influential than I am, what is Gordon Bell? Gordon Bell started on his business. So Gordon Bell, he was an architect of the QEP, he was a VP eventually at DEC, the CEO of a number of computers in this recognized around the world. And again, what he was saying is that this is the DARPA dilemma, is that DARPA directs purchases and screwed up the market, including many VC funded markets. There's no software. Users responded to the massive power with LCD software, clusters and clusters using APIs. So you see AOL clusters, you see all those Intels saturating the market, and these avant-garde architectures that and out of this, you say that you're not even addressing the problem. It's not these DLIW cores versus transputers, scalar machines versus vector machines. The problem is memory. So my philosophy is, what about, how do you solve this? And you all heard about Moore's law. Claims when Moore's law, the rate of expansion, transistor producing data, I thought was really interesting. When will the scaling of this technology come to? And the way to read this chart is, this is basically what the numbers. And you're seeing here the number of transistors per chip. You see the increase in the number. But the thing to notice here is that the clock speeds of these chips as you build bigger and bigger geometries and you add more nodes on the chip. The speed at which you run it doesn't increase. And you also see we're up to thermal constraints. So those two factors are limiting the overall performance that you get out of your device. So we have to rethink the way we're actually building devices. Rethink the way we actually build hardware and build software that runs it. This is what happens here is you see a lot of transistors, a lot of computing power on the chip, but it's not used. We run into things like dark silicon. So when will this diversity in the power curves affect the noise? When does this come to an end? And they look at several different problems, fellows, Todd Caldwell, Gordon Muir, a number of people, and ask them, when is it coming to an end? Technically and economically. And the prediction was earlier that we're going to come to an end of the scaling of all hardware. We're not going to get any more performance in the early 2000s. But that's not necessarily true. Gordon Moore actually made that prediction. He refined that just economically into a technical unit and said, we're going to hover around 2015 to 2025 when the scaling will come to an end. And a lot of people agree with it. We're on the verge of reaching the end of scaling of all hardware with computing. So some of the reasons are, if you look at the design cost, produce an ASIC or a CPU nowadays, this was done in the 28 nanometer. It's about $170 million. Why is it $170 million? So we're up here at $170 million. Well, there's an implied cost. You have to have a design team, there's front ends, there's back end, there's enclosure, the mass cost, all of the software, and the yield. And when you take into account the entire economy of building these reduced node geometries, and the other thing that's happening is that you can go down to a 16 nanometer chip or 10 nanometer chip, but you're actually defeating the Moore's law. You're actually paying more now per transistor than you did 5 years ago. So that's not going to work. So you have to do things differently. So all those laws, when things come to an end, you got to be careful. Because in the early 80s, there was a thing known as Grosch's law, which was computing performance increases as the square of the cost. Computer A costs twice as much as computer B. You should expect computer A to be 4 times as fast as computer B. A lot of people insist on that. Even Seymour Cray said, computers should obey the square law. When the price doubles, you should at least get 4 times as much speed. Well, that's not true. So these laws are switching from vacuum tubes to VLSI design obviated Grosch's law. And you can see that in the PDP 11. An $18,000 PDP Super Mini can outperform a CDC machine, legacy control data machines from just a few years back. So you got to be careful with these types of laws. Now, what I'm seeing is that primarily we've all heard about these types of things. Some people say it's about Neumann barrier. It doesn't matter what people call it. And I see this affecting a lot of different compute. GPU compute, DSPs, custom silicon, anything that involves a package with some circuits. As long as you have memory, you have a memory wall. And what you're seeing here is a number of different chips. You see Intel Xeon cores. server class cores on these triangles. And then you also see GPUs. You see NVIDIA GPUs and AMD GPUs. The y-axis here is the flops of y-axis. So this is the amount of computing power to the amount of memory that you use in moving data from remote to your computer. And GPUs produce more flops. Flops are free. They're all converging at this point. And what this is essentially going to see is, what this is telling you is that these lines are moving up. You're getting more flops on those transistors versus the amount of data that you move. Remember, this is a really big problem because if you believe the amount of data that is produced is growing and growing exponentially, you hear about big data, you hear about your camera, your phone, going from 2K, 4K, 8K resolution, your video systems at home, going from 1080p to 4K televisions to 8K, which will be predominant in 2020. The amount of data and the girth of data that we're producing at any moment is growing. You have a lot of data to process, but you're effectively not doing it very well. As soon as you get into your chip, you're doing well. But all that data, that growing amount of data, is a problem when you have a memory wall. So, what to do? This is my hammer at home. This is not the full sledgehammer, but I use this for a variety of tools. Steve, I can appreciate the value of having a sledgehammer. I would use this as my only tool.
Screwdriver.
Screwdriver? Yeah. If I could, I would. And essentially, you saw a lot of machines, a lot of these failures, saying that I have a sledgehammer and I can use it as a screwdriver. Well, that's not what I do. This is my garage. It's not a very big garage, but I have a lot more than a sledgehammer. The sledgehammer is over here. But I got some screwdrivers and wrenches and a ratchet set and compressor and all kinds of other stuff. This is what we need to do. You have to have more tools at your disposal. So I'm an advocate for heterogeneous architectures, and this is nothing new. A lot of people think that, no, I'm just going to make a heterogeneous machine, I'm going to put a GPU in my box, and now I've got something good. Well, sort of. My argument is that a true heterogeneous system will have a lot more tools than just a sledgehammer and a screwdriver. We'll see that in a second. So, some things that you have to realize when you're building a heterogeneous machine, you have limited resources. If you put all of these types of tools together, the CPU and the GPU, they all contend for memory. Your memory is your buses. There's a lot of things like if you have to worry about fixed function, ownership, deadlock propagation, and you still have this dark silicon. So you have to be really careful with heterogeneous machines. But a lot of people do. If you have a problem that has unpredictable code files, you're dealing with a legacy code base, and you have basically fine-grained codes, you put a CPU. CPU is very good at taking spaghetti code and running it. If you have code that has real-time requirements, or I should say a problem in real-time requirements, if you have a data flow that's naturally aligned with your application, so it's a streaming application, you push data in, you get data out. And you also have some avant-garde IO. Well, fixed function silicon, basically, problem basically is that memory is very high. If you have code that must perform small kernels of execution in very low power, you use a microcontroller. ARM microcontrollers. And these are very small, but they're purposeful. If you have code that, again, has real-time requirements, but you want it to be programmable, and it's a streaming application, and you're concerned about cost, well, then you might want to use a DSP or a And if you have an embarrassingly parallel problem, and your code can be multi, and you have this real nasty problem with vectorization, you go to a GPU. Well, that's how a lot of these SOCs are made. SOCs and ASSPs amortize the system cost, the power of board diagram, to a single diagram, so a single package. And the data flow is optimized for this. And here's the data flow, for example, quad-core CPU, a DSP, a fixed function silicon area, and a GPU, all attacking portions of a problem in a streaming media processor. This is an example of a monovelopage. What you see here is this is called an Armada 1500. This has a number of cores and a number of operating systems all existing on the same die, and it's purposely built. So if you have a cell phone, you have basically have a version of this car. But again, all of these suffer from one problem. And that problem here is this. They have one spigot to memory. This monster. So it's a time for some new technologies. So the early 80s were a really good time for being a computer architect. It's a good time now. So what are some of the trends that we see? And I want to talk about things like flash memory stacks, the more computing, dabble a little in managed language accelerators, computing memory, and computational memory. There's some interesting topics. We'll start with the machine, the HP. Look at that. That's a monkey. So the machine is basically a combination of persistent memory, optical interconnects, and near memory computing. So what the attempt here is to have a very large swath of non-volatile memory that acts and operates like DRAMs. So imagine if you have a flash system in your computer, and that was it. That was memory. The conversations about the machine, what if memory was, what if you never erased it? What if you had a program that allocated memory but never freed it? You just bought more memory. You could buy ink. Sure. That's a good conversation subject, but probably won't happen. What is happening is that they want to collapse the memory stack. So you essentially don't have DRAM and file system. You don't swap the base. You just have memory. And that memory backing, the media backing, is the HDDs. So the claim here is that, oh, we have this technology that will extend from the IoT space and embedded market to the exaspace. That's hubris. What they argue is that they're building an operating system based on what they call Linux plus plus. Essentially what that is a collapsed memory stack. So you no longer swap a page in, you simply have it. And it's designed ground up to address performance and security. So some of the claims here is when you collapse a memory stack, you can get obscene polymorphs. You measure things here in text, gigatext. So this is, you look at this, and this is your performance, your power, here in kilowatts, and columns. So what they compare themselves to is the IBM Blue Gene here, another massive super. And what they say is that if you have a very large problem, large amounts of data, because you have more data you can generate. And you compare the memory state to the Blue Gene, so the problem size is almost the same. Essentially, you can get similar performance to a multi-million-dollar blue gene computer machine for a fraction of the power. There's no longer DRAM. It's basically memory storage. You can get a number of cores, and you can make it very dense. And the whole problem here is that it's based on a memory store cell. And you have to fabricate a lot of memory stores to do that. The backup option here is the virtual phase change. And this is a mock-up of what one of these nodes looks like. That's not a real device. This is the claim from Micron. And essentially, they call it a machine. I call it collapse units. It's essentially what it is. And I think that there's some merit in that. Intel and Micron are sort of similar technology based on phase change. Another really interesting technology that is academic, and make sure that it has potential, is computing. And this is based on a memory store itself. And basically, this is the circuit. It's two resistors, and one resistor, and two resistors. And it's based on imply logic. So it's kind of a twist on normal Boolean logic. You look at it, the result is P implies Q. If P, then true can go to that result. So A implies B, and it's false. If and only if A is 1 and B is 1. It's a true function. So what good is that? Well, doing logical operations, such as these, can be done with imply logic. And you can get 1,000x performance improvement versus traditional computing logic, Boolean logic. You still need silicon to drive it. Everything's going to drive it. So you need something to drive this. And it's completely improved. So memory stores can be fabricated involved. But there's some air to this that is interesting, at least from a research standpoint. Another area is computational layout, and I call this data flow architectures. Data flow architectures, the systolic arrays, never really got a lot of support. There's a lot of academic treatments to data flow machines, but this is an actual data flow machine. And Micron actually produced a device called the automaton processor. It's based on a DRAM fabrication, but it essentially is a data flow. I'll explain what that is and why that's interesting. But it's fabricated and developed to address this memory. It's not memory. And it's actually quite good. The interesting thing here is that it only has 48,000 memory cells, 48,000 states. But you can do a lot of good and a lot of damage with 48,000 states. The power is pretty low for what it can do. It does require some pretty interesting computer science support. So, what can it do? So, if you're a computer scientist, you can do pattern matching, you can turn that in whole It's pretty impressive. So, here at Intel Xeon core, 2.4 gigahertz. The test here was, it was an edge traversal. The AP processor is actually about 10 times the performance of the at a fraction of the power, a fraction of the cost. So what does this thing look like? How do you program a data flow machine? Well, this is a data flow machine. And you program it in a series of states. Basically, it's a state machine. And this is the software that builds the binary that wiggles these transistors. And it's based on an impediment descriptor. So you create your states. This is very reminiscent of the sequencing. So instead of programming your machine with standard syntactical or correct language, you're actually programming it into series of states. It's comparable to what an FPGA would, but it's very programmable, and it can dispatch new states very quickly. So what is this really good for? Well, doing genomic sequencing in order of magnitude faster than a traditional computer. Doing pattern matching on a stream of incoming data. And instead of data going into memory, moving it into your cache, computing that, putting the result back into memory, it basically flows through this data flow engine and the result comes out. So if you're looking for threats on a network, you stream the network through the AP and you find your threats in real time. Computational RAM is a really interesting subject. I'm deeply involved with this. This is what I'm just showing here is some of the performance that you get out of computational RAM. I'm actually going to just talk about this. What this involves is not developing a state machine, not developing what HPs do, collapsing memory stacks, but actually using RAM as the method to compute. And there's been a lot of exercises in building machines. The IRAM machine was done for this purpose. So instead of moving data from memory to your compute, moving memory from DRAM into your ASIC, moving data from your DRAM into your GPU, you essentially use DRAM as a form of compute. Berkeley did something very similar to this. What these architectures look like is a connection machine, a machine that failed, in DRAM. And one thing you can do with this is get incredible and radical performance improvements. So if you look at this, the convolution. To run a convolution here takes about 17 milliseconds. And when this was published in the early 2000s, it took about 113 seconds to run a convolution on some Spark. So you see incredible speed of machines. Everything from 1,001 to 24,000 to 1 for doing things like a mass operation of imaging. So what good is this? Well, there's certain types of workloads you can process data incredibly fast because this completely addresses the memory. So I tend to think that something like this has some merit. Managed language accelerators. I threw this in here because this was a really interesting problem. Some people are still looking at this. There's a couple organizations and startups in the Valley that are looking at managed language accelerators. This basically takes Python and Java and accelerates it. So there's no need to JIT. You can improve your startup thing. And it reduces code information in the JIT process. It was not doing that. So if you're writing managed code, imagine accelerating that so you don't actually JIT it, you run by code instead of operate in the instruction set. ARM built a technology called Gazelle and about 140 Java instructions that were directly executed. 94 were emulated, and it was pretty small. So why didn't this do it? Well, it was a good idea back in 2004, but things that developed put it out of business. Because why? Who cares about your JITting performance? And it consumed a lot of registers. When you have mixed code, C or C++, managed code, it actually harmed. And then finally, we get into some really avant-garde stuff, neuromorphic computer engines. This is getting a lot of attention. The White House put out the Brain Initiative. This is not new. The whole idea with a neuromorphic computer engine was that it started in the late 80s, and it was built to address the von Neumann. It's based on deeply integrated player CMOS technologies. So what you see here is the IBM True North chip. And if you look at a human brain, it's a collection of synaptic connections and things. So the machine is very slow. It's not meant to be a traditional computing device, but it's made to be a very dense matrix of synaptic cores. So each core, there's 4,096 of them. There's 256 neurons, so if you do the math, basically there's 228 synaptic connections on the machine. And that's on a 5.4 billion transistor machine. Still a few yards away from the human brain, and a trillion synaptic cores, but it's interesting. Again, you don't program it in the natural language. It's actually a pretty difficult use of program. The memory units are tightly coupled to so IBM calls this the true North architecture. And the goals are here are to have 10 billion cores and 100 trillion connections, synaptic connections. Do it in 1 kilowatt of power. And do it in 2 meters of space. 2 meters of space happens to be what your brain is. So this is the brain engine. And IBM is charging for this. They made a claim, though, that they're going to take our architecture and it's going to scale to this. Oh. So, the other problem is that in dark so this is the first part is fabricated by HR Labs. They actually have silicon, so that's great. So the total government funding on this thing is $100 million since 2001. The timeline there is that they get to that 100 million core machine by phase 4, 2017, and that aligns well with these exascale Department of Energy goals that are also used. Well, maybe, but what's my prediction? Well, here's my prediction of these applications. So the machine, the challenge here is that they have a long way to go to Linux++ and collapse and they have to build memory servers and actually make them work. And I'm very doubtful that their architectures will scale down into 7. There's some like customer adoption, and it's going to have no penetration rate. What I do see successful is their optical interconnect. I think that is world class, and that could be used in the business by other manufacturers of interconnection chips. So I predict a lot of that technology in the business. Computed memories, so things like the AP processor. That's a difficult piece of program. If you're coming out with a CS degree, you probably haven't built a data flow program. So it's going to have a very unique industry that can master programming data flow execution. So the applications are a little uncertain. I mentioned things like security and networking, genetics and bioinformatics. That can be interesting. But it's a very dedicated program. And I don't think that's going to scale down into years. So the other aspect of computer memories is the imply logic, which is basically do see some very interesting results there. But that's going to be a decade away. It has to move away from academics into production system. Computational RAM, data flow. So, yeah, I can see that interesting. The APU is a little hard to program. But things like the Berkeley IRIN, I think those actually may have traction in the HPC market and some embedded markets as well. It addresses the memory problem happening. Managed language accelerators, I don't think that's going to happen. I think ARM is going to deprecate that technology, and I think that will exist, especially as you're constantly chasing managed languages and programming paradigms in general. And neuromorphic engines, there's a huge cost of innovation. And I don't think that can actually scale into anything that's practical that a GPU can do in GPU software. So it's going to be dedicated for a special purpose. IBM will not see super. So I'm a little tenuous in thinking that a lot of these architectures are going to be prevalent. I think some of them are, if they address the problem that's the industry's facing. So use the right tool for the job is my advice. And adopt heterogeneous architectures. So you're not going to stray away from that. You're going to embed whatever forms are necessary to tackle the job. And that's going to require a lot of software as well. Because you're going to have to take legacy code and divide it up into where it makes sense and into what core makes sense. Otherwise, you're going to constantly be fighting these non-running barriers in Moore's Law. You're going to level off the performance and your placement demonstrations. And you can't have humors that say that one of these architectures is going to do two. You've got to use the right job. Yeah? All right. Questions, comments, concerns?
So, Dick, you checked somewhat of a dark bias movement. So, just wanted to get your thoughts. Is there some way that the dark would change their behavior, or how would you see, or how do you think their behavior should change to be more realistic?
Well, DARPA has facilitated some of these select companies in the past and helped them basically get seed money. And those companies, like Thinking Machines, have contributed to architectures and to computer architectural paradigms that we use. So that's great. The problem I see is the complete reliance on DARPA to sustain yourself. So if you are building a product and you don't, your sole financial stream is DARPA funded, that's never going to work. You have to move yourself out of the DARPA model and wean yourself off of it and actually produce something for consumer or industrial or commercial purposes. The other they don't, but the organization that's working on the Synapse project completely relies on DARPA funding. There isn't a technology transfer path that's evident or hasn't been publicly evident to move that into their HPC market or their Z machines or anything like that. So a mature company would realize that and have the technology transfer to get it out into DARPA. I don't know what IBM is doing with that. Maybe they're doing the intelligent thing. The worst thing that they could do is rely on that and basically get comfortable with that document to support that division, to support that technology doesn't go anywhere. And so that will mean that that organization should yeah. I didn't. Oh, well, there is D-Wave.